Today we're going to talk about large aircraft planning calculations and charts. So first of all, looking at FAA test question 8630, I recommend you get out your green ASA ATP test prep book and you follow along as we go through these questions, and that you have a piece of scratch paper so that you can work on these questions as we go along, because working with them together, you will be able to understand how these questions work, and when you see them on the ATP test or on the aircraft dispatcher knowledge test, you'll be ready to do these questions, as well as on this test for this stage, which is going to include plenty of questions like this. So for this question, really we are looking at reading different charts, and we're going to step through this. So if we look at figures 56, 57, 58, the ground distance covered during en route climb for V3. A lot of the time you are not going to know exactly maybe how to do a question unless you study every single question. However, with some reading and looking over charts, which we'll talk about, you'll be able to understand how to actually do the questions. First thing I suggest when you're looking at a FAA figure is take a look at the whole figure. If we're looking at en route climb here, we are going to want to look at everything. We are going to want to notice that we have the brake release weight given in 1,000 pounds, so this would be 85,000 pounds. Cruise pressure altitude is given. Airport elevation is given, so that probably means something to us. Isotemperature is given. That probably means something to us. And the average wind component. That probably means something to us as well. So we are going to see that as we go on to the next few slides here. So first, make sure, remember we said we want to use the right chart, and we are looking at ISA. So we are looking at ISA, not ISA plus 10. When we look here, again, we said that we needed 85,000 pounds for our brake release weight. That was what was given in the previous slide. And the pressure altitude given was 35,000 feet. And then here we have information. This information is given in minutes and pounds, nautical miles, and knots. So we have 16 minutes, 26,000 pounds of fuel burned during this climb. We have 87 nautical miles that airplane has traveled to climb from airport to 35,000 feet, and the average speed is 373 knots. So if we look at this, we have 16 minutes with no wind and 87 nautical miles with no wind. If we took 87 nautical miles to go 16 minutes, 87 miles to go 16 minutes, and doing our calculator, we can say 87 miles divided by 16 minutes, and then 60 minutes for every hour. We get 326.25 knots, knot being a nautical mile per hour. All right, so moving on to our next part of our problem here. We have an average wind component, which is given to us in knots. So we're going to add our wind factor. If we have a headwind, that is going to slow our airplane down. So we calculated 326 nautical miles per hour, take off the 30-knot headwind, and we get 296.3 nautical miles per hour. So if we took 16 minutes from our climb, 296 nautical miles to go 60 minutes. Bring back my calculator here. We have 296.3 nautical miles in 60 minutes, since that's a knot, nautical mile per minute. Multiply this by 16 minutes, and we get that the airplane will travel 79 nautical miles during that climb. Moving on to an interpolation problem, we are going to look at figures 69 and 68. And here we're given an indicated airspeed and EPR settings for a holding scenario. The only problem is our holding scenario does not quite work with the chart as far as what altitude and what weight the airplane's at. So we are going to be having to interpolate in this problem. So for conditions 01, we have 31,000 feet of altitude and 102,000 pounds. Note these things for our next chart. So 31,000 feet, 102,000 pounds. Here's our holding chart. And you will notice right away we have 105,000 pounds and 100,000 pounds. And from our previous chart, we are at 102,000 pounds. So not anything right on our chart. So this is going to make us have to interpolate. And we also were told that we are at flight level 310, not 35,000, not 30,000. We're between the two. And we are supposed to find out our EPR setting and the airspeed. So for that, we're going to have to interpolate. And so let's just start simply. Let's start with our EPRs, and we're going to interpolate for the flight level 350 EPRs between 105,000 and 100,000 pounds. So with interpolating with this, we're going to do that first. So let me bring up my calculator again. So interpolating between the EPRs. So a quick refresher on interpolating. We need to find out the difference in how many thousand pounds we have. And we need to figure out the difference between our EPR settings. At flight level 350, 100,000 pounds, our EPR setting was 2.01. EPR meaning engine pressure ratio. So our EPR setting at 105,000 pounds is 2.01. At 100,000 pounds, it's 1.95. So we need to go up 2,000 pounds in our weight, up from 1.95. Okay, back to our interpolation here. All right, so first of all, the difference. So we can take 2.01 and we subtract 1.95. Those are our two EPR settings, and we get the difference between those two EPR settings, and we get 0.06. All right, now we know between 100,000 pounds and 105,000 pounds, there's 5,000 pounds of difference. So we can take 0.06, divide that by 5. We're doing 1,000-pound increments here. All right, so that's 0.012 difference in EPR per 1,000 pounds. At this point, we can multiply this. So we want to know 102,000 pounds. All right, so we take this 0.012, that was per 1,000-pound difference between 100 and 105,000 pounds. We take 0.012, multiply that by 2, since we want to know about 102,000 pounds, and we get 0.024. All right, and we remembered that from the previous chart, 1.95, that's our EPR setting at 100,000 pounds weight of the airplane. And we want to go up from that, up to 102,000 pounds. So we can take 0.024, add it to 1.95 EPR, and we get an EPR setting of 1.97. That's at 102,000 pounds at flight level 390. All right, so let's do that again for flight level 300. We go back a few slides. So at flight level 300, we've got EPR of 1.79 and 1.75. Bringing up my calculator. All right, bringing up our calculator. We have 1.79 subtract 1.75, 0.04 change in EPR per 1,000 pounds. If we divide it by 5, we have, that's 0.008 change in EPR per 1,000 pounds. We want to know about 2,000 pounds. Multiply it by 2, and we get 0.016. And we know we're up from 100,000 pounds. So we can add 0.016 to 1.75, and we get 1.77 EPR rounded. Now, that was a little bit of math. If you don't like math and you're better at estimating, you are welcome to take a look at this. And sometimes it's easy to interpolate just looking at it. All right, these are both odd numbers, 1.75, 1.79, 102,000 pounds is about halfway between the two, really. So you could also just estimate and say, all right, well, halfway between 1.75 and 1.79 is about 1.77. And that's what we came up with here, 1.766, which does round to 1.77. So at this point, we have our EPR of 1.77, and that's at 300,000, at flight level 300. So now, as one last thing, we actually have to interpolate between 1.97 and 1.77. The reason being that we said that our airplane's weight, or our airplane's altitude, was at flight level 310. It's not at flight level 350, and it's not at flight level 300. So to interpolate between those two, we're going to take 1.97, subtract 1.77, we get 0.20. We have an increment of 50 between 350 and 300, divided by 50, 0.004. That's per 1,000 foot of altitude between the two. All right, and we want to know about at flight level 310. So we can then multiply by 10. Since we had a difference of 50 between 350 and 300, we want to know about 310. Take 0.004, multiply it by 10. We get 0.04. And our low end of our EPR was 1.77. That was at flight level 310. So we're going to add that 1.77 to 0.04, and we get an EPR of 1.81. So that's 1.81 at 102,000 pounds and flight level 310. Now you would do the same exact thing for airspeed. Not necessarily that it's required, because only one of the answers in the test book, as you'll see if you're looking at it, has 1.81 EPR anyway. If we look back at here, we say to ourselves, does 1.81 even make sense? Well, we're close. We're about halfway between these two, 102,000 pounds gross weight. We are closer to the 300 flight level. So I would say that 1.81 does in fact make sense. So that's just a quick tutorial on interpolating. The question before this was really just interpreting different charts. So we're going to skip on ahead to question 8686 and look at a drift down scenario. So remember, drift down would be what level, what altitude is the airplane going to level off for its conditions on a certain day at a certain weight? What altitude is it going to level off if it has an engine failure in cruise flight? So that's really the question that this is asking, but it's a math problem again. So we're going to be looking at drift down for this question. So in this one, again, important to take a look, pay attention to the fact that we have a weight given to us for our engine failure happens in this one at 120,000 pounds. Our engine anti-ice is on. Our wing anti-ice is off. Our isotemperature is +20, and our air conditioning is off. So we're going to take a look at that as we move into the next diagram here. So we have this chart, it's figure 72. We're going to use this chart to find where the airplane is going to level off with our given conditions. Today, the anti-ice is on the engines, and on the wing, the anti-ice is off. Really important here want you to get used to reading notes. Important because our note tells us if engine bleed for the air conditioner is off below 17,000 feet, we have to increase our level off altitude by 800 feet. So before I even start doing the problem here, I'm going to take a look at that note. I'm going to file it away and say, okay, I need to make sure to read the notes. There are test questions the FAA has where you will have a right answer, you will not read the note, and you will get it wrong, which we do not want. We don't want that to happen. So always read the notes. All right, so in this one, if we are taking a look at, let's take a look at our gross weight and we also need to make sure that we are selecting the correct chart. In this case, we said that the engine anti-ice is on, the wing anti-ice is off. So we look at engine anti-ice on, top chart up here at the top. And then our engine failure, the airplane had engine failure at 120,000 pounds. And we said that the ISA, the deviation from ISA is 20, plus 20, ISA plus 20. So take a look at that, and we get that the airplane is going to drift down to about 8,800 feet. Now remember, we had a note. So what does that note say? That note tells us, that note is going to tell us when the engine bleed for the air conditioning is off below 17,000 feet, we have to increase our level off altitude by 800 feet. So is our air conditioning off? I'm not sure. Let's look back at the previous slide. And yes, it does say our air conditioning is off, that bottom line under D5. So air conditioning is off. In that case, we have to increase our level off altitude by 800 feet because our level off altitude here was 8,800 feet. So 8,800 feet is where we're going to level off. And we're going to add 600 feet. Oh, correction, 800 feet actually. I did not write that right on the note. And so we have 9,600 feet. So 9,600 feet, that is the correct answer. Moving on to the next type of question. This is figure 61 and 62. Our trip time for X1. All right, this is what is known as a spaghetti chart that we're about to see. And if you can follow a line, and you can follow a line with a pencil, you are going to be in good shape for this. So we are going to take a look at this conditions. Once again, I like to take a good look at this, what we're given as far as in X1, we see that we have a distance of 2,000 miles, a wind component given to us, we have a cruise pressure altitude, we have a ISA temperature, so this one's plus 10, and we have a landing weight. So all this is going to probably be feeding into our next chart, which you will see shortly. This is what's known as, like I say, a spaghetti chart. How this chart works, you are going to follow the lines. So can you follow the line? We hopefully can follow the line. I'm going to show you how it's fairly simple to do that. So first of all, for this question, we want to know the trip time. All right, we want to know the trip time. We have two different scales here. We have one that is for trip fuel. We have one that is for trip time. If we care about trip time, let's not worry at all about trip fuel over on this side over here. So, all right, for our trip time, we're going to begin our focus on the bottom of this chart. And we were told 2,000 miles was how far the trip was going to be. And we were told that we have a 50-knot tailwind. So looking at the bottom, we have 2,000. Here we have a headwind. Here we have a tailwind. And the reference line is if we have no wind at all, which is basically never. So we then go read our chart straight up from 2,000. If I were you, I would if you have not printed out this chart or you don't have the actual test prep figure book open to figure 62, pause this recording and go get figure 62. Either print it out off of a PDF if you're looking at that, or get your book out, because to follow this on a screen is not really what you're going to be doing in the class, or it's not really going to be what you're doing on the practical test with the FAA. You're going to have a paper test book, which is going to allow you to be more accurate. So pause it and go get that, and I'll hang out here while you pause it, and then we'll keep going. So 2,000 nautical miles, and we go straight up to our reference line, just right straight up to this arrow. But we had a 20-knot tailwind. So tailwind makes us faster. We actually go down following this line to about halfway between a tailwind of 100 and a tailwind of 0. It says we have a tailwind of 50. So we go down to the tailwind of 50. And then we read just straight up. We actually are ignoring all these lines because these lines here would lead us to trip fuel. We don't care about trip fuel right now. We only care about trip time. So we head straight up that line to our pressure altitude, and we can find our pressure altitude here on these different lines. All right, and then from our pressure altitude, which from what I'm seeing it looks like 27,000, we read straight over to our reference line. And again, we like to look at this whole chart. What's this reference line referencing? It's referencing our ISA deviation, -10, 0, 10, and 20. So for this problem in particular, we set a cruise pressure altitude of 27,000, and we have an ISA temperature of +10. So again, we've come up from 2,000. We've gone backwards to about 50 knots for our tailwind. We've gone straight up to our 27,000 foot pressure altitude line, and then we head over to our reference line. From there, we follow these lines a little bit down till we get lined up with 10. Coming up from here, from this scale of our ISA deviation, we have 10. And then we read straight over, and we find a trip time of close to just about 4 hours even. So that's how you use this chart. This is, again, called a spaghetti chart. So if you have still kind of catching your breath on that one, good. We've got another example to go. Let's do now using this scale, our trip fuel, for the same conditions. All right, so for conditions X1, we have a distance. Again, this is actually the exact same conditions that we just did. We're going to look back at our spaghetti chart and figure out our trip fuel. The bottom starts exactly the same, so that's easy. You can pat yourself on the back with that one. Straight up from 2,000 nautical miles. Remember, we've got a 50-knot tailwind, so there we can read back down on this line about halfway there to 50 knots tailwind. We read straight up, but this time we're not going to go all the way up here. We're going to read straight up to 27,000 foot pressure altitude. And looking down on our 27,000 foot pressure altitude, here's our intersection of those two lines. All right. Reading over here to our reference line. And now this scale we really haven't used yet, but it's for our landing weight. Here's our conditions given for conditions X1. Landing weight is 70, so 70,000 pounds. So we get to our reference line, and then we're going to follow these lines up till we reach our landing weight. So if we look straight up from 70 to about here, that's where we follow these reference lines till we get to that intersection of 70,000 pounds coming up. And then it's a matter of reading straight over here to get our trip fuel. It looks like just under 26,000 pounds for this one. So that is how you use this chart to find our trip fuel. We saw how to do our trip time in hours and minutes, and our trip fuel in thousands of pounds. This type of problem, it's looking at our trip time corrected for wind. And this type of problem is actually fairly simple because it's one of the FAA test questions that gives you the formula in the chart that you're going to be using. It's actually on figure 67. So take a look at figure 66. Here's figure 66, and we have a distance given to us and an average wind component. And then in figure 67, we are going to use those numbers to use this formula that is given to us here. And we can use that formula to take a wind correction because there's always wind. And then from that, we are going to be able to fairly easily figure out a correction to make. So for condition Z1, we are supposed to be finding our trip time. For Z1, here is our information. So 340 is our nautical miles. And we then find out our airtime in minutes and our fuel and our true airspeed. So we can use that formula that's printed on the chart. We want to know time. We want to know time corrected for wind. We have our time of 55 minutes, and we have our wind component. Today it's a 25 knot tailwind. Always like tailwinds. Always being smiling when we're having a tailwind. So we can take our time times our wind component and divide it by the true airspeed. And in case you don't remember, tailwind we do like because it allows us to save some time. We would add the time. If we have a headwind, we subtract for a tailwind. So again, really handy little formulas that are printed right here on our chart. Very helpful. All right, so let's take a look at that. We have an airtime in minutes of 55. And then we have a wind component of 25. So we can take 55 and using our formula on the chart, 55 minutes times our 25-minute tailwind, or 25 knot tailwind rather. And then we are instructed to divide by our true airspeed. And our true airspeed here is 438. So let's take this number, which we got by doing our 55 minutes of airtime times 25, we get 1375. And now we're going to divide that by our true airspeed of 438. And we get 3.1. Well, 3.1 what? This is actually 3.1 minutes. So are we going to add it or are we going to subtract it? It's a tailwind. It should have sped us up. So we're going to subtract it. So we have an airtime in minutes of 55. And we're going to take that and we are going to subtract the 3.1 minutes. So 55 minutes, taking away 3 minutes, 3.1 minutes, 51.9 minutes, rounding that to 52. So that would be how we do that. Now let's just repeat. Let's repeat this exercise and do the fuel consumption instead of just time. Let's do a fuel consumption one just to cement this information. Looking at operating condition Z4. Again, work along with me. That's going to really help you to learn how to do these calculations and get familiar with these charts and what we're looking for. Operating condition Z4, our distance of 290 nautical miles and our average wind component of 25 knots of headwind. All right, this time we got a headwind, so I'm not so happy. Sad face. But taking a look at this, we have 290 nautical miles to go. And we have a fuel burn this time of 4,950. Again, using that formula on the chart, this time we use the one for fuel. It's actually exactly the same, basically, other than we're using fuel numbers. So let's take a look at that. Bring up my calculator. And we'll do a little number crunching. All right, so we have our formula. Tells us the fuel, multiply by our wind component, and divide by true airspeed. So today our fuel for this scenario is 4,950. We're going to multiply by the wind component, which our wind component in this case is 25 again, except for it's a headwind. We'll get to that. And then dividing out by our true airspeed. For this altitude and this distance, we're at 443 knots. So we have this number dividing it by 443, and we have 279.34, and that's pounds of fuel. Notice down here we've got remember to add the fuel if we've got a headwind. That's going to make us burn more fuel. It's going to slow us down. So we have 279.34, and we can add that to 4,950, which we would have burned with zero wind. And we end up with 5,229 pounds of fuel for this. So there's our formula. We're going to add it because it's a headwind, and we get 5,229 pounds of fuel. All right, for this one, we're going to use another type of what I called earlier informally a spaghetti chart, and we are going to take a look at a radius of turn with a given airspeed and some information. So with this one, we're going to, again, pull out that chart. If it doesn't have chart figure 481 in front of you, pause this recording. I'll be here when you get back. Get that printed out or get your test prep book. So really need to have that in front of you. I recommend that you can actually look at that. So let's take a look at this. We have a reported temperature given to us. We have 500 feet above the ground, and we get an airspeed of 145 knots, indicated airspeed. Figure 297. What's that? Let's take a look at figure 297, and that is an approach plate. That approach plate is telling us an airport elevation is 5,355. So Albuquerque, New Mexico, fairly good elevation there. I'm going to make a note of that. It probably matters to us when we actually get to our chart. So if we look at figure 481 here, and I've repeated the question so you can refer back to that, but reported temperature of 0 degrees Celsius, 500 feet above the ground after takeoff, and an airspeed of 145 knots. What's our radius of turn? So we have to make sure, the problem told us 500 feet above the ground. We got our elevation from figure 297. It's at Albuquerque. So 5,355 feet airport elevation. Add 500 feet to that, and we're actually nearly at 6,000 feet for our elevation. And that's going to play into effect here. So for this type of chart, we are going to look at our outside air temperature. Again, I like to take a good look at what we have to work with. So we have our outside air temperature here. We've got altitudes given here and ISOs given up here. Got a reference line running right down the middle of this chart. And then all these lines here. In this chart, these are really lines that are essentially guide lines. They aren't representing anything. They're actually just guide type of lines. All right, so if we have a 0 degree temperature here, and we come straight up here, and we are almost at 6,000 feet of our altitude, so just about there, where those two things intersect, that's where we start going over toward our guidelines. So head straight over to our reference line. No matter what you're at here, you just go straight over till you get to that reference line. And then we are going to follow these guidelines up until we get to the appropriate indicated airspeed, read up from the bottom of the chart. So reading up from 145 knots of airspeed, and then straight over from there, we get a radius of turn, and if I take a close look at it, somewhere between 8,000 feet radius of turn. So this is in thousands of feet. This is in thousands of feet. So that's how we read that chart. This next type of problem is quite a long and involved FAA problem. I would have, again, printed out Especially, you're going to want the figure printed out that looks, I'm going to fast forward a bit here, like this flight log. I recommend having that printed out so that you can follow along with what it is that we're doing. So this type of problem, it is going to take a long time to calculate it. You can get a good answer and you can ensure that you get this question right. So the ATP knowledge test, the dispatcher knowledge test, they've got a lot of questions on them. No way to predict how many questions you're going to get that is calculation and how many are just memory items that you're going to learn. So I recommend learning how to do this question and being ready to give it your best shot on the test, the actual test. You have 3 hours. It's a lot of time. You should have time to actually run one of these calculation problems if you get one. So let's take a look at this and dive right in. So we're going to complete a flight log with this. We're going to gather some information first. First, we need to know our magnetic variation. And how are we going to get that? Well, we get, as one of our figures, an airport facilities directory for the area of Dallas-Fort Worth where our airplane is going to leave from. And from here, we can find out our magnetic variation is 8 degrees east. So that's good information to have. We need to note that. And then we need our true airspeed, which we can get off of our flight plan. We've got this flight plan form. That's what we got our true airspeed given to us here off our flight plan. And there it is. So we can use that information to work to fill out our flight log. So let's just file that information away just for a bit. And now we're going to actually look at that flight log. So if you haven't got that printed out, pause the recording, get that printed out. I recommend working along with this so that you can follow along. There's quite a few steps. So we're going to use information. We're going to have to get our distance for our leg, but thankfully they've given us a route. So here we have our route. We are going to go from DFW over to an intersection called Billy, and Billy to an intersection called Cougar, Cougar to, using the Cougar 4, and we've also got given to us our route of Victor 369. So we've got 2 routes, we've got fixes, we've got a arrival procedure that we have been given, and we can use all that in order to find our distance for the leg. Really, some of this is more about, can you read the information, can you find the information you need, can you use the FAA figures and guidance to get a good answer. So for our first leg, from Dallas-Fort Worth to leveling off, they give it to us. It's 27 nautical miles. So that's good and simple. Now we just need to figure out how far it is from Dallas-Fort Worth to Billy, whatever distance that is. We can take 27 away from that, and we'll find out this distance here. So let's do that. Let's take a look at how we're going to fill out that information. So here is one of the figures involved in this question. Victor 369, that was listed on our flight log. We've got it right here, Victor 369. So if we look at this figure, we have Victor 369 right here in the middle. We have Dallas-Fort Worth, and we're going to find our distance from DFW right here to Billy. So if we take a look at that, we have DFW, let's take a look here actually, DFW to Killer down here is 47 nautical miles. So, and I've kind of zoomed in on the chart here, but DFW to Killer is 47 nautical miles. It's actually labeled on this section too. From Killer, and if you haven't found this on the figure, pause this recording and find where we're actually looking at this. I had to zoom in to make it actually visible. From Killer to Torn intersection is 38. And then from Torn to Billy is 22. So we have got a total distance of 47 plus 38 plus 22, and we get 102 nautical miles. And then, since we had 27 nautical miles in our climb from the flight plan, 107 subtracting 27 out of that. We can do that. And we get 80. So 80 is how far we have, and that's what's going to be entered on the next line of our flight log. So we've written 80 in here, we had 27, and we calculated that this was 107 nautical miles. If you didn't find those intersections, take a break, pause this, go ahead and find these so that you actually know what it is that we're looking at, because we're doing a bit of a review of FAA charts as well, and in route charts in particular. Okay, so 27 and 80. Now we've got to get more distances. All right, we need to know the distance from Billy to Cougar, and then Cougar to whenever we start our descent. We know from the start of our descent to Houston, we have 25 nautical miles. So another helpful piece has been given to us there. All right, here's our Cougar for arrival. We've been told here to use the Cougar for arrival. Between Billy and Cougar, you can see we have 34 plus 13. So 34 plus 13 should be 47. We can enter that here. And then we have Cougar to starting our descent. Okay, we don't really know that, but we do know it's 25 miles from when we start our descent to when we are landing at Houston. So here we have a distance of 10 and a distance of 15. So we've got 10 shown right there, 15 shown there. So 25 to get to Mesa. And so therefore, if this is 25 and it's 25 to get to Mesa, we can naturally assume that we have 11 plus 10 to go here, and then this distance should be 21. All right, so now we've got all of our distances. That's a good thing. Next, we're going to have to take into account the winds aloft. And the winds have been given to us on here as 230 at 42. All right, so let's talk about the winds aloft. We said the winds aloft are given to us. That's great. We've got them given to us, and I guess they're at 15,000 feet. So winds aloft are always going to be given to us in true on a printed winds aloft forecast. So that's going to be given in true. But all these courses that we've been using, what we've been given on an approach chart like this or in route charts, we are actually given these in magnetic. And we need to have things converted to the same thing. I find it is easiest to just take your winds aloft. This is going to be opposite with some pilots, what you've been trained to do. But honestly, for the sake of easiness on these questions, this is what I recommend. We take our winds aloft and we're going to change these from true to magnetic, because our magnetic headings is what comes from all the other charts that you're using to get this information. So if our rule is east is least, west is best, we have Billy at 230 degrees true at 42 knots, which I had showed on the flight plan. Our airport facility directory, in our very first thing we looked at for data gathering, it told us that our variation was 08E, which means 8 degrees east. So 230 degrees true was our wind at Billy. Subtract 8 from that, east is least, west is best, and we get 222 degrees magnetic for our winds. We can use those winds to calculate a ground speed. Remember, all the goal of this whole problem was to figure out our total ground speed for this trip, or our total time en route for this trip. So let's take a look at the ground speed. So using our winds of 222 degrees at 42 knots, we're going to take a look at our course, 154 degrees. This is from figure 99 for Victor 369. I'm going to go back and pull that up so we can take a look at that. So here's Victor 369, and here's our course. It's printed right here, 154. All right, so we have that in magnetic. It's based off of a VOR, so that course is in magnetic. So we have 154 degrees on our chart. That's our magnetic course. Now we're going to use a flight computer to find what our ground speed actually is. Considering wind, using a flight computer with winds. So I'm going to do a demo of the flight computer. But first, let me show you somebody else who used a flight computer on the USS Enterprise, and that was Mr. Spock, who actually did use an E6B. I'm going to demonstrate how you can use your flight computer. This is a manual flight computer. This is allowed on an FAA test. The other types of flight computers that are allowed would be an electronic flight computer. That's fine for you to use. You cannot use a cell phone flight computer app or something like that. You have to use a metal one or a flight computer that is a electronic version just for flight computer type things. So here we have at our top of our true index, I've actually gone ahead and dialed in 222. That was what we calculated for the wind. I slide this down all the way to 100. Sorry, I slide my center section down all the way to 100. And we had said that our wind was 222 at about 42 knots. So I mark up from there, and you can see I've placed a little pencil dot and a circle. Hopefully you can see that right there. All right. From here, to use our flight computer to figure out a ground speed, we're going to spin our dial around to our true course. It was 154. We had gotten that from looking at our en route chart, 154. And now you can see that we have moved our wind dot that we marked around to the side. We're going to actually take this wind dot and mark on it our true airspeed of 248, which came from the FAA flight log that we got. So I'm just sliding it up to 248. And we can see once we've got it at 248, look over here and we can see that our center hole, there's actually the hole right there. Follow along with your flight computer. It's sitting right under 230. So I would say that our ground speed for this course is 229 knots. And then if we take a look at the next one, if we dial in a true course of 125 knots, or sorry, 125 degrees magnetic. Now, it's the same thing. We've got 129 and our true index at the top. We can actually just take our little slider and move it up to 248. Again, my pencil mark is at 248, about right there. I'm looking over here and I'm seeing my center hole and it's just under 250. So I would say that our ground speed for that leg is 248. We can note that on our flight log. Notice I'm writing this down on the flight log. Between the Cougar and starting our descent, it's actually still 125. And so our ground speed doesn't change. It's still 248. All right, now we can flip over our flight computer to the other side, and we can use this rate scale here, and we can use these scales to easily calculate our true air, our time for each leg. So let's do the first leg together. All right, so if our ground speed is 229 knots between level off and Billy, I'm going to actually take my rate. It says 60 there, and there's 220. We're going to look at the outside scale. Speed is always on the outside scale. Time is always on the inside scale. You can easily remember that by seeing how all these times in here have colons in between here. So we have like hours and minutes. All right. So right now I have my rate here. It's actually set at 220, but we said our ground speed was 229. So I'm going to increase that a little bit more. Up to right between, so this is 222, 224, 226, 228, 229. So that's now set. That's our ground speed for that leg. And we know from our previous calculations and looking at the en route chart that we have a distance for this leg of 80 nautical miles. All right. So if time is on the inside scale, that's what we're trying to figure out. Our distance is on the outside scale. And so what we're going to look at here, we find 80. If it gets in focus there. We have 80 right here on the outer scale. And we can read on the inner scale, opposite 80, we have 21. So we have about 21 minutes for that leg. All right, and I can note that on my flight log now. All right, now to do the next leg, our ground speed increased actually for that leg. It's up to 248 now. So we can take our rate indicator and turn it around to 248. I've just gone ahead and turned it down here to 248. Our next distance is 47 miles. So again, we look on the outer scale and we find a distance of 47. Let's take a look, and it's right under my finger. All right, so 47 for our distance. It's right about down here. So we have 45, 46, 47, and I am seeing between 11 and 12 minutes. So I would round to 11 and a half minutes. We usually want to round up as far as time or fuel goes. We do not want to run out of time or fuel. 248 again is set for that last leg. All right, and this leg distance is only 21 miles. So if we take a look over here, we've got 21 on our outer scale, time on our inner scale. So we're between 5 and 5.5 minutes. I would go ahead and say 5 minutes and 30 seconds or 5 minutes. So I've noted that on my flight log. Then we can add up each leg to come up with 63.5 minutes, hour and 4 minutes, and then the climb and the descent has to be added in there. We have a 21 minute first leg, then 11 and a half minutes, and then 5 minutes plus 14 minutes for our descent and 12 minutes for our climb. And so we get 1 hour and 4 minutes total. All right, if airspeed is ever given to you in Mach, which sometimes we have that happen, you can use this flight computer to figure out a true airspeed from a Mach number. And here's how it's fairly simple to do. So here's how we're going to do it as a quick tutorial on how to do this. We have ISA -6 at flight level 310. That's what's given to us. And what I'm going to do is say I need to figure out our temperature at altitude. A standard lapse rate is 2 degrees per 1,000 feet. If flight level 310 is 31,000 feet. So -2 degrees per 1,000 feet, and we get -62. So -62 plus 15, ISA of 15 at the surface is our standard ISA. And then, so 62 minus 15 is -47. So our problem, if we have a problem that tells us it's 6 degrees below standard, because we have a given of ISA -6, we have -47 minus the -6, we get -53. So that would be how we're going to actually get a temperature aloft. Next, we're going to use our flight computer to find true airspeed. And we actually have to turn the wheel pretty far around until we get to this little arrow right there. We actually have we have a Mach number index visible now. We have that, and we have -53 is what we've been told for a temperature. So here's -53, very approximately. It's a pretty fine scale here, matching with our temperature. And now on the inner scale, we have Mach 0.8. So Mach 0.8 is shown on our inner scale right there. And on the outer scale, opposite, we can read our true airspeed. And in this case, we get 454.60, about 464 knots.